On behalf of the Committee on Stochastic Programming, I welcome you once again to our webinar series, Decision Making in an Uncertain World. And today is the last one when we have a fantastic speaker, Katya Scheinberg from Cornell University. But I just want to mention that our webinar series, we've had a really great lineup of speakers from around the world. I want to thank all of them. And I also want to thank everybody who participated, from, again, all around the world, live, and also watch them on our new YouTube channel. And just because this is the last one, I want to thank again Vincent Leclerc, who suggested us to the Committee of Stochastic Programming to do this series. And also want to really thank my colleagues on the Committee of Stochastic Programming for making it a reality. Today, I'm joined by Wolfram Wiesmann, who's our webmaster, and he will be hosting this webinar. Just want to end with a very quick comment that if there's interest from the community, the committee will consider continuing this in the fall of 2020 or however long the COVID-19 pandemic continues, so that we can get together in a virtual environment. So, and with this, I will leave it to Wolfram.
Thanks a lot, Gaussian. So it's a great pleasure for me to introduce today's speaker, Katya Scheinberg, who is a professor at the School of Operations Research and Information Engineering at Cornell University, where she also serves as the Director of Graduate Studies. Prior to joining Cornell University, Katya was the Harvey Wagner Endowed Chair Professor at the Industrial and Systems Engineering Department at Lehigh University. And before that, she has also been a research staff at the well-known IBM Watson Research Center. She has done her undergraduate studies at Moscow University, and she has received her PhD degree at Columbia University. Katya's research interests are very varied, but they by and large span algorithms, both the implementation as well as the analysis for continuous optimization problems, including convex optimization problems, derivative-free optimization problems, as well as applications in machine learning. And Katya's research has received many accolades, including the Farkas Prize in 2019, as well as the Lagrange Prize in 2015. Katya is also very active in our community. At the moment, she serves as the editor-in-chief for our flagship journal, Mathematics of Operations Research, as well as a co-editor of Mathematical Programming. So without much further ado, Katya, thank you very much that you could make the time today to tell us a bit about your research. Before we start, however, we have the standard question that we like to ask everyone. Whether you could tell us perhaps a bit about your approach to decision-making and uncertainty.
Right, okay, well, thank you. Thank you, first of all, for inviting me. It's a great and interesting series of talks. I've attended some of them, and I very much aware that mine is a little bit of an outlier, but hopefully it will be somewhat entertaining. Yes, and the question is, when you first posed the question, I was like, are you asking me like in my daily life, or are you asking research-wise? Because we all live in an uncertain world, right? And so I kind of thought about it a little bit, and like, what would be my approach in daily life, right? What do I tell my children in terms of, I don't know, for example, choosing a career? And the kind of standard answer often is, don't put all your eggs in one basket, right? That's the approach to a certain world. And then I realized that, well, actually, I don't want to tell, especially when you're talking about a career choice or something like that, don't put your all eggs in one basket. Doesn't sound very good, because it's it just like means you don't focus on anything. So you want to put all your eggs in a very solid, robust basket, basically. And that's, in life, it's like choosing basically to work on things that are fundamental and will always be in need, right? And so in that sense, it leads me to kind of the topic of the research that I've been focusing on, and this talk will summarize some of these results. Basically, how robust are our baskets being algorithms, right? So we know, for example, something like stochastic gradient descent is extremely robust. Or maybe it doesn't put all its eggs in one basket, in a sense that it just throws in random directions in some sense and hopes like to progress somewhere, right? So maybe that's an example of not putting all your eggs in one basket, but being a little bit too spread out. Whereas our old kind of nice and classical algorithms such as line search and trust region that were reliable, and this is what kind of I grew up with, let's put it this way, in nonlinear optimization world, they are considered to be bad because essentially they do put all their eggs in one basket. They make a step assuming that things are deterministic, and if things go wrong, they're stuck, right? So that's basically what I've been working on for a while, is robustifying these methods and trying to see where, like, what the fundamental aspects of these methods can be robustified or robust in general, but keeping the essence of the methods as they are. Okay.
Excellent, thank you.
So
that leads very nicely to your talk, I guess. The stage is all yours.
Okay, thank you. Right. So this was my question. Okay, so this is the talk, it's a series of papers, and basically the talk is mostly based on the survey that we have written with, it's a short survey that we have written with Frank Curtis. It's appearing in one of the IEEE journals, I think for signal processing. And it's just, basically, it's going to be like a tutorial in analysis of convergence of several algorithms. And big part of it, I'm going to spend in analyzing convergence of deterministic algorithms, because it is a different way of looking at these algorithms. And once you see this way of looking at convergence analysis, it will be easy to transition to the stochastic part of it, right? So essentially, first I'm treating an algorithm as deterministic one, and I'm actually going to talk about different algorithms, but I'll talk about one framework. And then I will switch to the algorithm being a stochastic process and just switch around a few concepts and explain how things extend. Okay, so I kind of already gave an introduction to the idea, but basically what has been going on is that the new applications that have arisen in the last 10, 15 years are causing us to pay more attention to problems that are stochastic, or on such large scale that in terms of like large sums where, you know, sampling is essential. We are also interested in solving problems inexactly for various reasons, because we can't solve them exactly, or because inexactness somehow serves as regularization. And the methods that have been created specifically for, you know, these kind of settings are not very satisfactory. And the kind of more classical adaptive methods that have been designed for exact deterministic optimization are not obviously usable. So here we're trying to basically take the adaptive standard methods and see how usable they can be for this new setting. And the emphasis will be on complexity analysis of these methods rather than, say, implementation, simply because this is one of the focus of, you know, latest research, is that, you know, can we reach certain expected complexities? Okay, so I'm talking about unconstrained optimization. We will assume whatever smoothness we need on the function. It's standard usually for depending first or second order method that you use. Typically the functions will be non-convex unless it's specified specifically, and then it's we will look at three methods that are designed for deterministic function: line search, trust region, and cubically regularized Newton. So basically, the idea is, can we adapt them, right? Can we move them to a new setting? All right, so now I'm going to try to go slowly. My slides are a little dense, but luckily I have this laser pointer that I can use. So here is the generic adaptive deterministic method framework. I have some step size parameter. I have some parameters that I need to separate. I have a starting point. And most importantly, I have a model. So at any iteration xk, I build a model, and for a while we'll think of it as just Taylor series model, first or second order, standard stuff. And I'm going to take a step that depends on the step size somehow. So the step size determines how far am I going to go. I'm taking a step, and this step is going to improve my model. So I have to make sure that my model at the new point is better, right, than the old point. Then I check if the same thing happens to my function. If my function indeed improves along that step, not along that step, but specifically once I take that step at this new point. And so this is the adaptivity here, is that I will take that step if I am successful, if this reduces sufficiently. If I am not successful, then I will not take the step, and I will change my parameter, usually by reducing it, right, by some constant. Moreover, if I'm successful, I will increase my step size. So when you talk about line search, you don't necessarily look at it exactly this way, but essentially it can be cast in this form. Thrust region is usually used in this form, and so is regularized Newton. So basically the point is that if you're successful, you think you can be more aggressive in your steps, and if you're not successful, you have to scale back. All right, so just to be specific, and some of you, you're probably familiar with line search, you may be less familiar with thrust region and even less so with regularized Newton. So if you're talking about line search, usually we have some kind of a approximation. Typically we have, so we have the exact information on the function, the gradient, and then some Hessian approximation, which can be just diagonal. And so we can minimize, but it has to be positive definite. We can, it's a convex quadratic function. Its minimum is achieved at this point, sorry, H inverse this, but then the step size alpha k is involved. It's called damp Newton. Well, that's not necessarily Newton if this is not second order Hessian. So basically this is some kind of a step which is meant to be in the descent direction. And so in principle, if the step is not long enough, this Armijo condition will be always satisfied. And so that's exactly the condition on sufficient reduction, right? And we kind of know that under these conditions, things are all good. So if it's not satisfied, we don't take the step. If it is satisfied, we do. So the trust region method, you again have some second order approximation. Now, no longer H has to be positive semi-definite. It can be exact Hessian. It can be something else. And instead of minimizing this function, because it's no longer positive semi-definite, so therefore the function can be non-convex, you minimize it in the ball of radius alpha k. So this alpha k here is the radius of your trust region. And again, you will minimize the model, therefore the model will improve at the next step, but the function does not necessarily improve. So you check if the function improves compared to the model improvement. And this is your sufficient reduction condition. The specifics of these conditions, they're traditional, they're classical, they have their reasons behind them, but we don't necessarily have to focus on them. So cubically regularized Newton is a very interesting method because it basically grew out of the trust region method, but it has the advantage of having optimal convergence rate guarantees. And that is because it has this kind of nice twist. Instead of minimizing the model in the ball of radius alpha k, it adds this cubic regularization, which kind of doesn't constrain your step to be exactly in a ball, but clearly does not let the step to go very large, because if alpha k is small, then this coefficient is large, this term dominates, and so you're not going to go very far from the current iteration to get a minimum. And for the methods to achieve its optimal complexity, you need the exact Hessian computation here. Well, I mean, I'll tell you how. It doesn't have to be exact, but standard original method required the Hessian to be present there. So this is a second order approximation. Okay, again, you minimize this model. Now it's unconstrained and it has a global minimum. Depending on various assumptions and conditions, you need a global minimum, or you can get away with a particular local minimum. And then there's a sufficient reduction check again. So you compute a step which reduces your function, your model, and then you check if it reduces your function. If it does, then you take a step or not. Okay, are there any questions at this point? Okay, so the classical picture is basically either you're going along, so here in blue is my model, it's just a linear model, in red is my function. I am trying to minimize the model, I take a step, and either my model is also, sorry, my function is also decreased, or if I step too far, like in this case, because I have a curvature in the function, I may end up with function actually increasing, right? So these are the only two things that can happen. Okay, right. So how do we now analyze convergence of these methods? So there are some moving parts here because there's a step size that changes from iteration to iteration. And there is basically, it's like what will happen on some iterations when the step size is large, what will happen when it's small, and so on and so forth. So it's a little bit messy. And there are techniques for each of these methods how to prove things. But so here's the framework that we kind of propose, which at first looks a little unnecessarily complicated, and it is maybe for the deterministic method, but it encompasses everything. So let's focus on this for a little bit. So here I have this phi k, which is essentially some kind of a Lyapunov function. It's a function that will be decreasing with iterations, okay? So it's a progress of an algorithm. It's not necessarily the function values. You'll see it's not exactly going to be function values, because not always function values are improving. These WKs are basically sequence of indicators which say if iteration is successful or not. So if we have taken the step, WK is 1. If we haven't taken the step, WK is -1. This is for convenience because now we can express exactly our relationship between alpha k plus 1 with alpha k. This is the step size parameter, and we know that it goes up by 1. Sorry, it gets multiplied by gamma if a step is successful, and is divided by gamma if it's not. So therefore, this WK is either 1 or -1, just as described above. All right, and then finally, we're defining a stopping time. Again, this is not a stochastic process, but still we can say, we can call it a stopping time, and that's the first iteration where we reach the desired accuracy. So we reach the accuracy epsilon, and that accuracy is measured depending on the situation, either by gradient value, norm of the gradient becoming epsilon, or if you're converging to second order stationary point, it's the gradient and the most negative eigenvalue, or in convex cases, it's the function minus the optimal value of the function. Okay, so this is basically, right, so this is what happens, what we define. And this is the condition that is going to be satisfied by all our algorithms. And if it's satisfied by all our algorithms, we can then apply the conclusion. So we'll have a condition, and then under this condition, which will be absolutely trivial, we'll have kind of a theorem. So let's see, what is this condition? So we have this process, the progress of the algorithm, the step sizes, these WKs. And here's the first essential condition, that alpha k has this very particular property, or the algorithm has a very particular property, that there is a lower bound value, we call it alpha underscore epsilon, which depends on epsilon possibly, such that, so it's the smallest step size after which all iterations are successful. So that's essential for optimization algorithm. For deterministic algorithm is to say that, okay, if I'm cutting my step sizes, if I'm adaptive, it has to happen that when my step size is small enough, I'm always successful. I'm guaranteed to progress. Okay, and so this is the property we require of our algorithm. And then the next property is that on every iteration, this phi, whatever it is decreased by some amount proportional to this alpha k. Not necessarily, well, it's a function of alpha k, let's put it this way. So some function of alpha k dictates the progress of this thing. And by the way, this phi k has to be non-negative. So now we start somewhere. We cannot make it negative. So very obvious conclusion is the total number of iterations until the accuracy is reached is, sorry, this is, I think, yeah, right. This is not very clearly stated that all of these conditions hold until T epsilon is reached. So if on every iteration we have to increase by this amount, and alpha k cannot possibly be smaller than this, that means that on every iteration we decrease at least by this amount, and so the total number of iterations cannot be bigger than this, simply because phi 0 is where we start, we decrease on every iteration, and we cannot pass 0. Okay? Are there any questions about this? So that's kind of the essence of the the analysis, and it's, you know, it should sound simple at this point. I hope it does, because that's kind of the idea. Now to the specifics. So how does this work for every specific algorithm that we have in mind? So for line search, for non-convex functions, our stopping time is when gradient goes below epsilon. The function, the phi k, this Lyapunov function, is a combination of the function gap, so how far you are from some lower bound. This is just so it's non-negative. So it's something, it's a function value here, times a coefficient. And then also this term here. Now, why do we have this term here? This is because essentially on iterations when the function value doesn't change, right? Because we have unsuccessful iterations, alpha k decreases, so therefore this whole thing decreases. On the iterations when the function does change and we take a step, this part decreases. This may increase, but there's a balance between the two reached by appropriate choice of this nu here. And that's where things get technical. But basically here is exactly what it is. On successful iterations, we know that the function is improved by this amount. So it's a gradient squared times the size of the step. That's what we're guaranteed. And on the unsuccessful iterations, the function is improved by this much. And so we put these things together and basically get what we want. And from what we get is the number of steps is bounded as 1 over epsilon squared, which of course is the standard complexity bound on gradient descent. It is standard complexity bound on both gradient descent and any line search method, first order line search method, basically. This, okay. Right, so now trust region. Similar idea, the function, the gradient has to be below epsilon. This Lyapunov function contains simply the trust region radius squared, and again, the function improvement. And again, it comes from the fact that on successful iterations, we're guaranteed this much improvement in the function, which is trust region squared. And so we balance it out with the improvement on the unsuccessful iterations, find, you know, the appropriate mu to balance things out, and get the complexity bound of epsilon to -2 again. Okay. So regularized Newton is a similar thing. The key here is slightly different guarantees on improvement on the function, and that's really essentially the kind of the genius of the cubic regularization, but we're just here to use it. So we are going to again construct appropriate Lyapunov function, which comes from the fact that when the steps are successful, we get this much improvement, which is you notice it's not gradient squared as before for line search, it's gradient to the 3/2, but it's a gradient at the next step. So when we are, when we've taken the step, the next iterate, it's the value of the gradient is that. And then you, again, balance it out with the unsuccessful steps. And this is exactly what gives you, because you want the gradient to be above epsilon. Sorry, you trying to reach the step where the gradient is below epsilon. So you assume it's above epsilon until you reach that point. Therefore, you have the complexity of epsilon to -3/2, which is the optimal complexity for non-convex optimization. Okay. There are other examples one can work with. So you can do second order trust region method. As I said, converges. This time you will be converging to a second order stationary point, which is dictated by this quantity being below epsilon. You'll construct the appropriate Lyapunov function. You'll get complexity 1/epsilon to -3, which is again standard. You can get line search for convex functions and for strongly convex functions. And again, you recover the standard complexity. Okay, there's nothing new here, just a different way of looking at things, because so far we've been dealing with deterministic functions. Okay, so let's now look at the stochastic function, or rather stochastic case. So we have an adaptive stochastic method. What is stochastic here? Basically, all the information about the function can be potentially random, right? So you can have function values that are random, the gradients that are random, and the Hessian estimates that are random. So what is random is this model, MK, okay? And what is also random is the estimates. Remember, when we're checking for sufficient decrease, we compute function values and see if the function value has improved. We no longer have access to the function value, we only have access to its estimates. So here is the key difference in the algorithm that I'm looking at versus, say, standard stochastic gradient descent method, is that I will require some accuracy of, I would not want just these estimates to be true in expectation. Moreover, I don't actually have to have them true in expectation or exact in expectation. I just, so they don't have to be unbiased estimates, but they have to be sufficiently accurate estimates with some probability, okay? So I will talk about the requirements for quite a bit. And this framework, again, admits a lot of different assumptions, but these assumptions, they are generally stronger than just standard stochastic gradient. On the other hand, maybe I'll talk about it a little bit later. On the other hand, so just let's focus on the what is different here. So we have a random model, and therefore, when we're computing the step is random. And we basically, when you think about it, because it's a random model, you may not have a descent direction, right? This model may not be accurate at all. It may not be at all an accurate representation of your function. So what it gives you can be, not good at all. Also, you have these function measurements that can also be faulty in principle. And so here you're also not sure what you're getting, but the algorithm actually pretty much runs as it is. There are some changes to the actual algorithms to make things work that we needed to make. They're not very significant, but there are some. But the spirits of the algorithms remain. And then the framework is still such. Okay, so here are possible different assumptions on the model. So some of these assumptions have been used in the literature, and some of them not in my papers, but in other people's papers. So this is becoming a common way of, estimating gradients and Hessians and assuming certain accuracy. But some of them, I believe, are nicer than others. So for example, so G is our gradient estimate now. F is the function estimate, and H is the Hessian estimate. They're all random. One standard, well, not so standard, but one assumption I've seen in the literature is simply to assume, since we are aiming at the accuracy epsilon, that the gradient estimate will not differ from the true gradient by much more than epsilon, with probability, some kind of PG. Now that's all good. I would claim that this is another not adaptive assumption, because it basically first you pick epsilon and then you require this accuracy. But in fact, when gradients are large, your algorithms do not need to be as accurate as when they're smaller. So this epsilon is really required when your algorithm is close to the epsilon accuracy, but it's not really necessary. This assumption is too strong when you're further away. So you can have this sort of condition, which works under some algorithms such as stress region. So you have a step size here. And if your step is large, then your accuracy does not have to be very tight. If your algorithm, if your step size is small, which means that you're possibly closer to convergence, you require more accuracy here. Again, everything with some probability. And then so on. So we have other versions here. This is the step size for line search. So again, if steps are large, less accuracy is required. Here is an interesting, very useful, but not always feasibly implementable condition, that the accuracy is actually proportional to something, to the norm of the gradient. Now, you don't know the gradient, so it's not very clear if you can actually achieve this. But in some cases you can, and that's basically this sort of condition with theta equal less than 1. It's a guaranteed descent direction. And finally, we also need conditions on the function values. And again, you can just plug in epsilon here. This time you have to do it epsilon squared, because you need more accuracy in the function values, simply as Taylor series would give you more accuracy, higher level of accuracy in the function values, and other different types of conditions. Okay. So depending on the algorithm and the analysis, the least things that you should require is that these probabilities are greater than half. So essentially you have, well, maybe their product, actually not a comma, but their product has to be greater than half. But usually PF, so the probability of the accurate functions has to be larger than, larger than PG. So what does it mean? It means that you kind of, these are constant probabilities. They don't have to go asymptotically to 1. They depend on Lipschitz constants and other things. So you can tolerate failures, and you can tolerate more failures in the gradients than in the function values, or more frequent failures, let's put it this way. And mind you, again, none of these conditions are just in probability. So we don't necessarily saying that these are unbiased estimates. Moreover, for many cases, we don't need to know what happens with these estimates if they don't satisfy this. And that comes in handy in some applications, because we cannot always estimate and bound the variance, for example. We can only bound this norm and expectation. With some probability. Right, so here are suitable examples. So one way of computing random gradients without actually having a stochastic function is this Gaussian smooth gradient introduced, well, probably not introduced, but kind of analyzed first time by Nesterov and Spokojny. And this is for black box function optimization, for example, gradient-free optimization. But in general, it's a interesting way of approximating gradients. So here you don't see any gradient information. You just take function values. The functions are assumed to be exact, but they don't have to be. You can extend it to noisy function values. And the matter of fact is that you can establish this bound. So with high probability, this estimate approximates the true function, the true gradient, with this bound plus a small term, a term that can be made smaller by this parameter. Okay. Then there's a standard way of approximating gradient and Hessian by just Monte Carlo averaging. which is what people do in the machine learning community typically. And then you just simply have a bound on the variance of the stochastic gradient simply because you're using sufficient number of samples, and you can ensure whatever right-hand side you need here, and then from that get the concentration inequality on your for just this difference in probability. Finally, there are other ways of approximating Hessians and gradients. So there's sketching, and there's sparse Hessian recovery, and then there's robust estimates for cases with outliers. And again, many of these results give you a bound in high probability, but not necessarily an expectation. And this is, this is still applicable in our setting. Okay. All right, so now I'm going to basically introduce the kind of the concept of like what goes wrong compared to deterministic case, and how we deal with it by adapting the framework that I've introduced with phi and these W's and whatever to the stochastic case. So we have now the blue is again our model, red is our function. The model is random and it can be inexact, like in this case, can be very inaccurate. It's no longer a Taylor series expansion, but these red triangles are the function estimates. So here are the two cases when the function estimates are good and the model here is good and here is bad, right? So what happens here is that good model, good estimates, we come here, we see that the function has improved, we take the step, it is a successful iteration that actually decreases our function. So that's the ideal situation that we want. Now here is model bad. We take the step in this direction, function estimates are good, saying, oh wait, the function is actually increasing, don't take the step, recompute your model, reduce your step size, and so on. So here we kind of erroneously reduce our step size. So we shouldn't have reduced it if we had a better model, but we did it and we just, we don't know that we have a bad model. We think we have a good one, but we may have a bad one, so we reduce the step size, fine. I'll move on. Here is another situation where actually the model was good, but we erroneously thought that it wasn't because we computed the function estimates badly. And here we missed an opportunity to take a step and reduced our function our step size parameter instead. So that's again kind of a missed opportunity. And here is a nasty case where the model is taking us in the wrong direction and the function estimates are bad, so they are telling us to take that step. So here we actually take a step which we shouldn't take, and that actually can increase our function, right? So we no longer have the guarantee that the function always decreases on successful steps, it can increase. And so the properties of our algorithms or algorithmic framework are not the same. So here is basically the framework, let me remind you. So phi k was this general form of Lyapunov function. It's a sequence for every step. It's a, some kind of value of that function, and it's a random sequence, right? WK is a random indicator sequence, so it's either 1 or -1, depending whether this iteration is successful or not. The step size parameter still behaves the same way, meaning that if WK is 1, if the iteration is successful, alpha k increases by multiplying by gamma, otherwise it's divided by gamma, so this relationship holds. And now T epsilon is a stochastic process stopping time, so it's when our algorithm has reached the desired complexity, desired accuracy. Okay, right. So what is true about this new stochastic process? So as I said, it's no longer true that phi k decreases on every iteration. So we do not have this. So this is what's written here is what we had before. And what we had before is that this decreases by a certain amount proportional to alpha k. That's no longer true for every iteration. Also, what's no longer true is that the iteration is guaranteed to be successful if the step size is small enough. Simply because we can have a completely inaccurate model or bad function estimates, which means that we may not be able to have a successful iterations even when the step size is small, and so it may even get smaller. But what is true is the following. So we basically have this condition 2 says, okay, I'm going to draw this here, specifically left some space. So the alpha k is the value of the step size parameter, which increases, and it's kind of symbolically, it's multiplied actually, but if you look at its log, that's what you'll see. So it increases on some iteration, then it decreases. Let's say it reached the value, and this is our alpha underscore. So this is the value which, for deterministic algorithm, beyond which it cannot go. It's going to go up. But now we will be able to go down because we do have occasional decreases. We can go down, we'll go up again, we'll go down, we'll go up again, we'll go up, and so on. And the key thing we require of our algorithm is that whenever it's below that threshold, it is a random walk with a positive drift, or geometric random walk in this case. So that means that we are basically more likely to increase the step size than decrease it. And that is the key assumption, because basically what it means is that even though my step size can get smaller and smaller, in theory, it is unlikely to do so. It's going to be recurring to this value every so often. And the next assumption is, instead of saying that our function phi decreases on every step, it simply decreases in expectation. So if we balance out whatever can happen on each iteration with appropriate probabilities, and we can show that in expectation there's an decrease, then this is sufficient for our analysis. So with these two conditions, with these two conditions, we are able to prove the following theorem. So if these two conditions hold until the stochastic, until the stopping time occurs, then this is the bound on our stopping time, expected stopping time. So the expected complexity of the algorithm is bounded by this, which is, this is exactly the same as it was before. So this is basically, this is, starting value for phi. This is the guaranteed decrease in expectation in every iteration. And this is the probability term. And so this probability is basically, as I said, we're more likely, like in this case here, we should be more likely to go up than down. That means P has to be bigger than half, and that manifests itself here. So if P is bigger than half, then this is a constant term. Okay. Are there any questions? Is there a question? I'm just gonna give the summary of the results, and
sorry.
Okay, so I'm gonna skip these. These are specifics for every algorithm. So basically, it's the same framework as I gave before in some ways, and the phi's are pretty much determined in a similar way as we did before, but there are some intricacies, especially in case of line search. But again, you define the phi, you define the T epsilon, and your alpha k is your trust region parameter, and then you essentially, you have to prove that the properties that I just described for this phi and alpha k, they hold. And this is the hardest part. I mean, the hardest part is to make sure that in expectation, this quantity decreases on every iteration. So you have to pick your probabilities properly and things like that, and make some proper assumptions on the inaccurate models, on the gradient and Hessian and function estimates. But once you do that, you get a guaranteed so you get expected complexity bound, which is the same complexity bound as deterministic method times this term, which depends on your probability of success. Same thing for second order trust region. Again, you get 1 over epsilon cube here, same term here, line search, more complicated way of deriving the function. So it's not just very straightforward. You have to add some terms here. You have to fiddle a little. We get this L cube here instead of L. That's the Lipschitz constant of the gradient. That is probably an artifact of the proof. Don't think we really need that. But 1 over epsilon squared convergence is recovered. Same thing for convex case. 1 over epsilon this time for convex case. More complicated design of Lyapunov functions. Strongly convex case, log of 1 over epsilon, just as usual. So everything is good here. And here is basically what I'm working on right now. This is here we hit a wall. So this is cubically regularized Newton, and that's the interesting open problem. And simply because, simply put, because the T epsilon is the moment when your next step is has the gradient below epsilon, not your current step. And crudely speaking, this is not a stopping time of a stochastic process. Therefore, you cannot use the Walls identity that we use to derive our complexity bound. And so we have to kind of develop different tricks to try to avoid this. So this has not been properly answered yet. Okay, and so this is basically, we like this framework because it seems to be relatively versatile, but there are still some gaps with it. There are actually other people who have been adapting the framework. Just to put a little bit perspective, there has been a lot of works recently where stochastic methods basically have sufficiently accurate gradients and Hessians and function values in the assumption. And then the analysis performed as if the algorithm is a deterministic algorithm under the assumption that good things happen on every iteration. So I just want to emphasize the contrast of what we're doing here is that we are not assuming that good things happen on every iteration. So this is a solid, complete analysis that gives you the expected complexity bound, not just, bound with some probability. So this is the key difference in some sense what we're trying to do. And yes, we're trying to analyze the standard adaptive algorithms that come from old optimization literature, but I'm not sure this framework has to be limited to that. It's just that that's what our focus right now is. And with that, I thank you for your attention. Here are some references, and I'd be happy to talk to you more about it.
Thank you very much for this talk. Very interesting. We already have a number of questions, actually. Soroush is asking a few of them. Let me perhaps read them out so that we have them on the video as well. The first question is how to set the underline alpha epsilon for general convex and non-convex objective functions.
Right. Is it possible to extend result? Right. So, first, yeah, the question about, so we don't need to set it, right? So this is the nice thing. Here granted, I completely skipped over the, the usual analysis, sorry. Let me go back. Where did I go through the analysis? Here, for example. Okay, right. So I didn't get into the details of this, right? Yeah, I don't actually have. Yeah, very good question because I totally skipped over this. So if you go in a standard, let's say, deterministic analysis of a line search method or whatever, there is a specific alpha bar. Underline alpha bar, underline alpha epsilon, that is actually in line search, it does not depend on epsilon, but in trust region, it will. it will be proportional to epsilon. So there is actually a quantity, and you prove that below this quantity you cannot go, because every time you hit this below this quantity, your iterations are successful, so your alpha goes up, right? So you don't have to set it, it's just automatically there. Your complexity bound certainly depends on it, but you don't need to do anything. It's just that's how your complexity will work if you have high Lipschitz constant. I mean, in some sense, the most trivial example is in line search. Alpha is, alpha bar is 1 over L in the most standard sense. So if you take a gradient descent, so if you take gradient descent and you take step sizes of smaller than 1 over L, well, maybe gamma inverse, because you are, you may go a little bit below, but basically if you can never go below this value. So if you're below 1 over L, you will always have a successful step. Okay, so L is a Lipschitz constant, you don't know it, and that's the whole point of the algorithm. You don't need to know it, it'll just automatically kind of self-correct once you're small enough. Okay, one more question.
There was one more question from Surush, yeah? Mm-hmm. Whether this extends to constraint optimization problems.
So this is a very good question. We have, so clearly the algorithms themselves are, they're designed for unconstrained problems, right? But usually for constrained problems, you kind of turn it into an unconstrained problem to some degree, and then, well, often. But anyway, in terms of unconstrained problem, you also measure progress, right? So I do believe it is very possible. It's just that, yeah, I mean, we haven't gotten to this yet. I think the framework itself should be adaptable to this. Like, you measure progress, if you're guaranteed progress and expectation until you reach certain accuracy, this whole framework should apply.
Great. There's a question from Robert Bassett about the slide with the upward drift condition.
Mm-hmm.
And how the condition on the alpha k, how that relates to how practitioners often choose the step length.
Well, okay, so that's a whole other thing, right? So if practitioners are choosing step length by themselves, that is not what we're talking about, right? Because we're talking about algorithms that adaptively choose step length. So this is basically, yeah, I'm suggesting to look at algorithms where you don't have to dictate the step length, but you can afford to let your algorithm choose it for you, except for, yeah, so this upward drift basically has to, like, back to this alpha underscore alpha bar, there has to be this value below which you don't need to know it, you don't need to set it, but it has to exist. This value below which you're guaranteed that you'll have successful steps, right? So you don't need to choose the step length, but you need to make sure that your algorithm gives you sufficient accuracy. Now, if you, like, for example, if you use stochastic gradient descent without sufficient accuracy in the gradient, this is not going to work, because what will happen is that you will very likely have really bad gradient estimates, and this alpha k is going to shrink to, not alpha, not this one, but alpha k is going to shrink too fast and too far, and yeah, you're going to have tiny steps. So that's not good. But if you have more, so this has to be combined with the sufficiently accurate gradient estimates, especially function value estimates, as a matter of fact.
Great, that seems to have answered the question. Very good. There's another question from Surush, who's asking whether the analysis can be adapted to study the convergence behavior of accelerated gradient descent algorithm.
Yeah, so it's an excellent question. I don't know how to do this, because the analysis of accelerated gradient algorithms is very specific, and it is not. So the algorithm that I described here, you can show there that some kind of improvement happens on every iteration. And in accelerated gradient algorithms, from you know, what I know, it's some kind of a telescopic sum that you eventually obtain, and then terms cancel, right? So you don't necessarily get improvement per iteration, and therefore bound on the number of iterations, but you get an improvement over collection of iterations. And how to translate it to this framework is not clear to me, because at least, you know, when I looked at it a few years ago, I didn't see how to do this. But yeah, I would be very interested in, you know, thinking about it.
Excellent. Uh, there is another question from Soroush. Let's see. He promises it's his last question. Let's see. He showed a convergence in expectation, the vanilla stochastic gradient descent for convex problems. You can get high probability results. So basically, the question is: would you think it's possible within your framework to also get results in high probability?
Yeah. You're right. I mean, yes, and for some specific cases we actually do, or other, maybe not necessarily us, but it's actually almost obvious, except for we just didn't sit down to write it out. So when you do this analysis, okay, so here is, and yeah, I've been kind of thinking of like just getting some students to work out not just this bound, but the bound in high probability. So essentially, all we want is for this process to have a high probability bound instead of just the expectation bound, right? So I mean, there's an obvious way to do high probability bound. It's just that if on every iteration everything is good, then you will have a deterministic bound with probability that everything good on every iteration, right? So probability of having good estimates on every iteration is high, then the compound probability of all of them gives you probability of everything definitely converging, right? So that's first thing. It's like automatically there. But there is more than that. Basically so how do we obtain this result? This result is obtained because we're basically saying that we get this expected improvement per iteration as like a sub-martingale argument, and then every so often we're back at this value or higher. So the alpha bar is not frequently below this. And so for basically, I mean, in some sense, what you can do is you can kind of discount, so how frequently, so the number of steps by which you may exceed this, by which you may exceed this bound, it happens because you make mistakes and you have basically unsuccessful iterations with alpha that is small. So you shouldn't be having it, but it can happen. And so essentially, to have this number large, you need to keep on making mistakes, which is exponentially, basically it's the exponential decay in the probability. So you could probably put the analysis there relatively easily to bound this T epsilon and expectation. I mean, again, we haven't worked it out, but I think it's just sitting there in the stochastic process.
Excellent, very good. So that is perfect. It's also perfect timing, given that it's now 4 o'clock. Thank you very much again, Katya, for sharing these insights with us. It's great. I think we as a community, I think I'm not in a position to speak for my colleagues here, but I believe that sometimes in our community, we know far too little about the algorithms that we're using to solve problems. So it was very good to get an idea of recent research in that field. So thank you very much on behalf of all of us. This concludes today's seminar, and it, as Gaussian was saying, it also concludes the current row of seminars. We will consider whether to continue this seminar series and how to do that in terms of timing. It has been a big success so far. It's great to see that we still find ways in these difficult times to come together, at least in an online fashion. If there's nothing else from your side, Gaussian, I don't know whether you wanted to make any announcement or if.
Yeah, I think I'm good. Thanks again, Katya, for this wonderful talk.
Thank
And
you.
again, I want to thank all our speakers and all the people who attend our talks, seriously from all around the world. And yes, so Bernardo at least votes for the series to continue. And yeah, we will talk with the committee and hopefully make it a reality again. And if you have any suggestions, please feel free to reach out to the committee and follow us on Twitter, LinkedIn, and watch our seminars on YouTube.
Okay. Great.
Thank you very much, everyone, and have a nice weekend.
Thank you.
Thank you. Bye-bye.
Bye.